All right, so on page 237, we looked at some of the information about the inverse yesterday. Now we've got a graph. It says sketch the graph of the inverse on the same grid. So some important notes that we've already put down, but we'll put them down again. What do we do with our points? With an inverse, we switch the x and y values. So what does that mean? Well, on the red graph here, we've got the point 3, 2. So that means on our inverse graph, we're going to have the point 2, 3. On our red graph, we have 1, 3. So now we're going to have 3, 1. Here we have -1, -1. If we switch those around, those points stay the same. We still have -1, -1. And finally, on the red graph, we have -4, 4. So now we're going to have 4, -4. So as far as finding our points, all that's going to happen is our x and our y values are going to switch. Now, sometimes when you've labeled those 4 new points, you might wonder, well, how am I going to connect them? Okay? You might be able to remember which points were connected to which points. So you might be able to say, well, we did this one first, and it's connected to this one, so I know this needs to go down there. That might be one way that you figure out which ones are connected to which ones. But the other thing that's important with an inverse graph is to know that it's a reflection over the line y equals x. So if I draw that as a dotted line here, I'll do it in green. Y equals x is a straight line. It's a diagonal line with a slope of 1 and a y-intercept of 0. And now if you can imagine taking that red graph and flipping it over that green line, it might make sense how to connect your dots better. So one, you can remember how to connect your dots by just saying, well, which points did I do in which order, and connect them that way. But you can also see that if you reflected that over that line, so everything that's above the line gets flipped below that line, and everything that was below that line, like the point 3, 2, got flipped up above the line. Now, sometimes flipping on a diagonal line is difficult, but on the final exam, you are allowed to cheat by turning your page sideways just a bit so that your diagonal line is a horizontal line. They'll never pick this up. And then you can just flip it over a horizontal line, which is much easier. I can't turn the whole smartboard here right now, but do you get the idea? If you turn this sideways so that your green line was a horizontal line, it would be much easier to visualize flipping it over the horizontal line. Flipping over a diagonal line seems difficult to do, but as soon as you turn it horizontal, it makes sense that, oh yeah, that I can totally see that point going straight across to that one. And they'll never catch you on the final exam if you turn your page a little bit sideways. A couple of other things to notice. Where do these graphs intersect? Well, wherever your points were on that original graph, were on the line y equals x, when you flip it over, those are the points that are going to stay the same. We had one of those as our key point, -1, -1. But we see that there's another point where they intersect. So sometimes when they're marking a question like this, they're looking, have you drawn a dotted line for that diagonal line to show what you're flipping over? And then have you taken care to make sure that these 2 points where your original graph intersected that dotted line, that your new graph intersects that as well? Now for part B, is the inverse a function? How do we tell if something is a function or not? What do we know about functions? Functions pass the vertical line test. So is ours a function? No. What does it mean to pass the vertical line test? The vertical line test says if you drew a vertical line, there's a vertical line, and you took that vertical line and moved it across your graph, if it ever hits your graph more than once, so can you see that right now it's hitting my blue graph at 2 points, then it will not be a function. Can you see that our original red graph is a function because no matter where I go, I never hit the red graph more than once. So the red graph is a function, but the blue graph is not. I even have a point right here where it hits 3 times. But you just have to find one place that it hits more than once, and then you can say it's not a function. So our blue graph is not a function because it doesn't pass the vertical line test. Finally, it says state the domain and range of the function and the inverse. So our original function is red, so I'll do that in red. Our domain, our smallest x value is -4. Our largest x value is 3. I'll write it in set notation this time. So our domain is between -4 and 3. And our range, our smallest y value is -1. Our largest y value is 4. And then for our blue graph, if we look at our blue graph, our smallest x value now is -1. Our largest x value is 4. Our smallest y value is now -4. Our largest y value is 3. What do you notice? Compare the domains and the ranges. They just got flipped. So this idea right here happens everywhere. It happens on the graph, you switch the points. It happens in the domain and range. All we had to do was switch this x to a y, and we had the range. We switched this y to an x, and we had the domain. So switching the x and the y values, it happens when we want to graph it. We can do it with individual points. It happens with the domain and range. We can just switch the x and the y values. And it's also the way that algebraically we find the equation. Step 1, you switch the x and the y values, and then solve for y. Questions for practice are 4 and 9. What we're going to do this morning is we're going to do the first 3 questions, then I'll give you some time to work.